Question 8. Capsaicin is found in the chili peppers, and this is a structure. And you should assume the CH3 group is unreactive in this question. Part A. Name all the functional group in this capsaicin in addition to this CH3O group. So other than this CH3O, so what we can see is amide group here, CONH, and the CC double bond. When you answer, you just write CC double bond like this. And another one is the phenol. Do not put hydroxyl group. So this is one group. So this is a phenol group, and it's inside your syllabus. Right? So you have to give these three: phenol, amides, and CC double bond. For part B, complete the equations for the reactions of this capsaicin with the excess bromine in dark. So this one is telling us that the bromine will added to the CC double bond. So it's the electrophilic addition that you learn in AS. So means it will react with this CC double bond, and each carbon will get one bromine. So to form this part. Right. So this one, CC double bond will react with the bromine water and form this part. Of course, the bromine will not just react with the CC double bond, it will react with the phenols here. Okay, we know that the phenol is direct 2,4,6 substitution. So the phenol will react with the bromine, and the electrophilic substitutions will happen. And let's say this is the first carbon, so second, the carbon, fourth carbon, fifth, sixth. So the second and the fourth carbon already there is a substituent there. So therefore the bromine will just directed to this carbon. Means for this carbon it will be the bromine. Means the bromine will substitutes the hydrogens in this CH. So means initially here is one hydrogen, and the hydrogen being substituted by the bromine. Right? Okay. In a simple way, we say that the OH can direct the bromine to this the sixth position. So now we know that it's going to involve 3 bromine. Means here 1 bromine, here 1 bromine, and here 2 bromine. So it needs 3 bromine, okay, for the reaction, and of course it needs to use 2 bromine molecules. So another bromine will combine with the hydrogens that release here, the hydrogen ion, and form the HBr. So therefore total 2 bromine molecules needed, and eventually will form this organic compound together with the side products HBr. So this one is a balanced equation, right? For question C, capsaicin is heated with excess hydrogen gas in the presence of platinum metal. The 6-membered ring reacts in the same way as benzene under this condition. So now again it's telling us these molecules will undergo hydrogenation. So the type of reaction is reduction, which means for the compound, okay, this compound, okay, this is larger. So we know that this CC double bond will get saturated by hydrogen, this part. And we know that in benzene ring there are 3 pi bonds, 1, 2, 3. Of course they are delocalized. So these 3 pi bond also will get saturated, means hydrogen will saturate this double bond in the benzene ring, and together with this. So therefore, what you will get is this cyclic. So you get this this one. So you get this cyclic. So the benzene ring now is from the cyclohexane. So means all the double bond here, the 3 double bond just now has been saturated. And of course, the cis double bond just now also being saturated. So it will form this compound. Okay, and this part D. So when this compound is treated with reagent J under suitable condition, one of the products is methylpropanoic acid. This one. Identify the reagent J and any necessary conditions. The methylpropanoic acid is obviously from this part, means this part. So this CC double bond need to break, and this part will form the methylpropanoic acid. Okay, because after the bond break, we need to use hot concentrated acidified KMnO4 under this condition and the reagent used. So this CC double bonds will get oxidized. So this part now it will form, okay, this carbon will form COOH, because this carbon with one alkyl group and one hydrogen. So after the oxidation, after the bond break and oxidation, this carbon will form COOH, mean is this one. Together with this alkyl group, so it will form the methylpropanoic acid, right? Again, this one is first carbon, second carbon, third carbon. So this is methylpropanoic acid. Okay, so for D part 1, of course, we know that reagent J must be hot concentrated acidified KMnO4. Okay, part 2 is the proton NMR question. There are 3 different peaks in the proton NMR of the methylpropanoic acid in this CdCl3. Now, table 8.1 is given the environment of proton, examples, and the chemical shift. So you have to use this table to answer. Of course, you're not going to use all this environment of proton, just use a few, and you have to choose it. In order to do that, so you need to know the structure. So let's say now it's better for you to, if you are not familiar with proton NMR, you can draw the display formula, and it's easier for you to see the splitting pattern and the chemical shift and the environment of protons. So now is asking CH3. So the CH3 it's which group? So we need to look at this. In this methylpropanoic acid, the environment means the CH3 here is means this one. This one. This CH3 and this CH3. In order to get the splitting pattern, we need to see the how many proton on adjacent carbon. For these 2 methyl group, the adjacent carbon is this one, and it has 1 proton only. So these 2 methyl group as one group, so 1 plus 1, so you get 2. So means the splitting pattern is for this methyl group, this methyl group, and this methyl group. After coupling with this proton, you get doublets. So means you see doublets like this. Right. So splitting pattern is doublet. And of course, this chemical shift is the first one, alkane. So environment of proton is the alkane. Example is this one, right? So because this methyl group is next to another hydrocarbon, means another alkyl group. So it's basically alkane. So therefore, the chemical shift is alkane, right? So that's why we choose the first one. Chemical shift therefore is 0.9 to 1.7 ppm. So you just put there. For the methyl group, because it's next to another hydrocarbon, so it's basically alkane again. Chemical shift is 0.9 to 1.7. Splitting pattern is doublet. Okay, explanation is very easy. Why it has this doublet? Okay, because the adjacent carbon has one proton. See, one proton on neighboring carbon. That's your explanation. It's just because of one proton only on adjacent carbon, it's coupled with this and this methyl group, so 1 plus 1 is 2. So if you get doublet. Okay, another one is the CH. Now we need to switch the position. Now we need to focus on this proton, means the CH here, right? So for this CH, now we need to know which proton will couple with it. So we need to go to the adjacent carbon. So these are the adjacent carbon. On the adjacent carbon, it has 1, 2, 3, 4, 5, 6 proton. So means this proton will couple with this 6 proton. When this proton, okay, which is 1, couple with 6, so 1 plus 6 you get 7. So means you get 7 peaks. Normally, when it's more than 4, you actually can give multiplet, or you can actually put heptad. Heptad means 7 peaks. And the chemical shift for this CH is what? So you have to look carefully, because the CH now is actually bonded to 2 groups. One is alkane, another one is CO double bond, means the carbonyl. So when the CH, or when this hydrocarbon, so it's bonded to CO double bond, then we need to use this one. When the alkyl, means in this case is the CH, when the alkyl is next to CO double bond, its chemical shift need to be 2.2 to 3. So means for this CH, because it's bonded or next to CO double bond, this one, the carbonyl. Actually, this is carboxyl, but we just look at this, right? So therefore, its chemical shift, okay, it must be 2.2 to 3, according to this table. And of course, it's multiplet, I told you just now. So what is the factor, or what is the explanation for this multiplet? Because this proton, again, this proton is coupled with this 6 proton on the neighboring carbon. Your explanation is very, very easy. You just need to say that because there are 6 proton on neighboring carbon, means this carbon and this carbon has 6 proton. Okay, the last one is the COOH, which is this proton, which is this one. And this proton actually has no coupling, because no adjacent the adjacent carbon has no proton to couple with, and this H is not really bound to a carbon. So means it's going to follow the last one. When the proton is in the carboxyl group, so its chemical shift is 9 to 13, right? So therefore you get this chemical shift. And because no coupling involved, means this proton is not going to couple with any proton, right? Not like others just now. So therefore it stays alone. So it forms singlet, 1 peak only. So therefore the splitting pattern is a singlet. Okay, I hope you understand on this proton NMR. And let's move on to part E. E1. So this compound, the similar compound now, is heated with excess of hot NaOH. So remember, this is in excess. So when it's in excess and it's hot, the hydrolysis might happen. And in these tables, it's actually telling you that it's formed two organic products. So we are quite sure the hydrolysis of this amide will happen. Okay, means these amide bonds will break and it will form two compounds. So since here you see nitrogen, so means the H will be mostly from this part. And of course the K is from this part. Now, what you need to know is after reaction or after hydrolysis, what will be the following reaction. Okay. If let's say now hydrolysis of amides happen, you need to understand first, this CO will form COOH. So means this carbon will get OH and this nitrogen will get H. Because hydrolysis means it need to involve water. So one will get H, one will get OH. So this will form amine, this one will form carboxylic acid. And this amine is a base, means it will not react with the NaOH. Only acid will react, right? So in this structure, in this part, the one that will react with the sodium hydroxide is the phenol. Because we know that the phenol is a weak acid, it will react with the sodium hydroxide. Okay, for example, let's say now we have one phenol like this, will react with sodium hydroxide, form the phenoxide, sodium phenoxide and water. So basically it's just a neutralization. So means base, acid and base form salt and water. Okay, so therefore this part means this part, the phenol will form phenoxide, means this one will substitute by the sodium ion. So it's from the sodium phenoxide. So means your answer here this one. So this one is wrong. Okay. So again, this one is a phenoxide. Yeah. So mistake here. So this is a phenoxide. Okay, that will be formed. And this one no change, and this one of course no change. Right. So this is the compound H. After you do this, so you have to count the carbons, hydrogens, and the nitrogens number. So if it's same as this, then it's correct, right? Okay, so for this K, then we need to look at this part. So after hydrolysis, this one will form COOH, as I told you, and these CC double bonds will not react, means it will form this. After hydrolysis, it will form this, and because this is carboxylic acid, so it will form the this carboxylic, means this salt. So the sodium hydroxide will react with this carboxylic acid to form the carboxylate. Right. So remember, okay, this one is the this salt, COO negative, right? And this is the sodium. And of course, this part no reaction. So again, if you want, you can check with the carbon, hydrogens, and oxygens and the sodium number. Okay, part 2. Name 2 types of reactions occurring in E1. So first is what is the reactions that involve is hydrolysis. Okay, I told you already, hydrolysis of amide. So second thing is the acid-base reaction. Okay, this one, the phenol with the sodium hydroxide is the this neutralization reaction or acid-base reaction, and for this carboxylic acid and sodium hydroxide also acid-base reaction. So that's why, okay, the 2 types of reaction is hydrolysis and acid-base reaction. Okay, part F. Draw the structure of the organic product L formed when this capsaicin is treated with the lithium aluminum hydride in dry ether. So this one you have to understand, when we use lithium aluminum hydride, it can reduce the amide. Reduce the amide. Means the lithium aluminum hydride will react. Okay, let me delete this one. Means the lithium aluminum hydride will reduce amide here. How they reduce? It will remove oxygen and after that add 2 hydrogen. This is how it's reduced. Means this part you see CH2 after the reaction. The rest no change. So that's why you get this structure. So means just now the CO double bond, right? So it's now changed to CH2. So the others part remains unchanged. Okay, if you want to know how the equations looks like, so this is the reducing the reduction equations for this amide. So amide will reduce this one. This oxygen will removed, and after that 2 hydrogens needed added. Sorry. So this H2 will add to the carbon. So eventually amides after reduction it will form amine. And of course you need to use the hydrogen with the square bracket and balance the equation. So of course it will form water. The O will combine with H to form H2O. Okay, so that's all. Thank you.